right, what questions from homework do we have? Chapter 14, 1 through 20 is the first set of Chapter 14 problems I assigned. Which one is yours?
Number 14.
Number 14.
Are we supposed to use multiplication rules?
Yes. You are. So in number 14, it says you're to be part of a group of 3 students from an intro stat class that was described in problem 12. 55 have never taken calculus, 32% have taken 1 semester of calculus, and then the rest have taken 2 or more semesters of calculus. Usually in other classes across the county and across the country, AP Stats is usually considered after a calculus course, that's a typical progression. But because the College Board only requires Algebra 2, and that's really the only math you really need, then that's why we offer it as early as 10th grade here at Stonewall. Anyway, so if we look at question 14, it says neither of the 2 students has studied calculus. So we need to probably think about what the probabilities of each are. So we have no calculus, we have 1 semester of calculus, or we have 2 or more semesters of calculus. So let's go through those percentages again. It says 55% have never had calculus, so we'll say 55 or 0.55. We're going to change it to a decimal. And then it says 32% or 0.32 has had 1. What does that leave me with to have 2 or more semesters? All right, so what is left with 2 semesters of calculus, guys? What's left? 13%, right? They have to add up to what? 100%. So we know that much. Now if we go ahead and we got those percentages from number 12. So now if we're looking at 14, it says that your other 2, let me read the question, sorry. You are assigned to be part of a group of 3 students, okay? And so I have 3, and it says, what is the probability that of your other 2 group mates? So we're only looking at the other 2, not you, right? So we're looking at 2 people. I think that was a little confusing in the question. You're a part of 3, so we're only worried about the other 2 right now. That might have been part of the issue. But if we look at the other 2, it says the other 2 people neither had studied calculus. So that is right, that is the multiplication rule. The first person did not have calculus, and the second person did not have calculus. I tend to use the words and or a lot because and means multiply, and that implies the multiplication rule. Now, we're going to talk a little bit more today about whether those are independent or dependent events, but they're going to be independent events because whether or not the first person didn't take calculus has no bearing as to whether the second person had calculus or not. So it's going to be 0.55 times 0.55, and if you just, or 0.55 squared, you multiply those 2 things together, what did it get? 0.3025? Good so far? Okay. And we look at part B, for problem 14, it says both have studied at least 1 semester of calculus. So we have to be careful, okay? The probability of at least 1, now, it could be this, they could both have this. Let me show you all the different possibilities. So, we could have the first one having 1, the second one having 2 or more, or the first one having 1 and the second one having 1, or I could have the first one having 2, the second one having 1, or they could both have 2. There's all different kinds of scenarios. I think that's too confusing. So I think the better way to look at this question would be to use the complement. Remember how we talked about that at the end of class last time? At least 1 is the same thing as 1 minus the probability of none. Remember how some of you got your phones out, you videoed that part? Put it like that. The complement is 1 minus none is the probability of something. Okay, at least 1 is 1 minus none. That, and honestly, if you can get that out of today again, that's what you need to get out of. Okay? Or we can try to come up with all the different possible scenarios, which is a little bit harder to do. So I think the complement here is the easiest thing. We know what the probability of none is, don't we? What is it? Okay. So we can say 1 minus 0.3025, which becomes probability at least one semester of calculus? At least one minus one. Did I do something wrong? Hunter?
I did it,
The way that the book does it is this. I'm gonna do it the way the book does it in a minute. I just need to make sure what I'm doing wrong.
I think I did the way the book does it, just first term, so second term, and then try.
That's what you did. Yeah. It's 0.45 times 0.45 is what the book says here. I'm just trying to figure out why the complement doesn't work. So at least one is 1 minus none. 1 minus none. Oh, duh. You know what I'm doing? I'm having a moment. 1 minus none is 0.45 or 0.55, so it is 0.45, right? 0.45. Sorry, I'm having a moment. That is the complement. There's two of them. 0.45 times 0.45 is what I'm looking at. So 0.45 times 0.45 is 0.2025, and that is correct. Okay. Any questions on that? Is that what you're talking about? Yeah. All right, and then part C. Let's look at C. C says, what's the probability that at least one has had more than one semester of calculus? Okay, so at least one, well, we have the same thing I have highlighted here, right? So at least one is the 1 minus the probability of none. So we need to figure out the probability of both having none, right? So let's look at that. So the probability of none is 1 minus the probability that neither had any calculus. Let me make sure what it says here. At least one has had more than one semester. So more than one semester would be 2 or more, right? Is that the way I'm reading that? Double check me on that. More than one. More than one would be 2 or more, right? Okay. So probability at least one had 2, at least one or more. Okay, so probability of at least one or more. So if we think about that in terms of all the scenarios, right? At least one. The first one we don't care about, right? It could be none and 2. Or we could have 2 or none. With me so far. Okay, or we could have 2 and 2. Or we could have, there's all different kinds of scenarios. We could have 2 or 1. We could have 1 or 2. And there's at least one or more means that at least one of the pairs has to have a 2. At least one of the pairs. To me, that's too confusing. So I think that you need to use the complement. Rather than try to create all of the scenarios, I think the easiest thing to do here is to use the idea of a complement. So, make sure I'm writing the words down here. So, at least one has more than one semester of calculus. More than one. At least one has one or more semester of calculus. Okay? So, let's try to figure out how I could write this as a complement. This is the question. The probability that at least one of the two people, could be the first person, could be the second person, but at least one of those two people has one or more semesters of calculus. How can I use the complement to use this, to rewrite this idea? What would I do? You guys tell me. Do you understand my question at all?
No.
Okay. Did you understand what I was doing with the pairs of 2 a second ago? Some yes, some no. When you're looking at a group of 2 people, okay, I can say at least one of those 2 people, could be the first one, could be the second one, has to have 2 or has to have one or, is it one or more than one? I keep saying more than one. That's what I'm getting confused about. More than one. More than one one semester of calculus is 2 or more. Would you agree with that? Okay. So we're really kind of focusing on this situation. Are we okay with that? Did you have a question, Hunter? Okay, then go ahead and tell me how to write it. Sure.
1 minus 0.0169, because that's the probability that they're going to 0 semesters.
Well, I'm not worried about 0 semesters. What I'm looking for is the complement of this. Okay? So if I want the probability that neither, let me say it this way. The probability at least one has more than one semester of calculus is 1 minus the probability that they don't have 2 or more semesters. Okay? Let me say it one more time. I think we have 2 and 2. We have 2 people we're worried about. Okay? We'll worry about the 2 people in a minute. We have no semesters of calculus, 1 semester, two or more semesters. Right now, the question's asking me, what's the probability that at least one of the 2 people falls into this category? Okay? Well, rather than try to come up with all the different ways I can group those 2 people, it could be the first person, it could be the second person, it could be both those people. We don't care what the other person is doing. So what we're going to rewrite this as is 1 minus both of these people have not taken 2 or more semesters. So what is the complement of 2 or more semesters? What is don't have 2 or more? What's the probability? What number is associated with that? 0.87. So that is what goes here. The wording bothered me too. I would say the wording bothered me at the beginning when I kept reading the problem over and over, where it says more than 1 semester of calculus. Is that 1 or more, or is that 2 or more? I think that's where I got lost too, to be honest with you. But I think I would try to be a little bit more clear with the wording on a test or a quiz. I would say something like, what is the probability that at least one had 2 or more semesters of calculus? I'd be more specific. Okay? Because that would definitely. But let me show you, well, first of all, what's the answer here? What, 2431? If I wasn't going to use the idea of the complement, which I don't think it's not natural to think that way. So I understand that that's not your first thought process. If I tried to come up with just all of the different ways I could do this, this is what I was doing before. So if I lost you what I was doing before, now I want you to pay attention. Okay? So, I have groups of 2 people, okay? I want that at least one of these 2 people has to have more than 1 semester, which means has to have 2 or more. So I'm going to say that 0.13 goes here. Would you agree with that? Is that probability that is associated with 2 or more semesters? Yes, no, maybe so. Okay? Is that the only way that means at least 1? Could you have both of them have more than 1 semester? Okay, so we have another scenario here where they both have more than 1 semester. You're with me so far? So we could have one of them, or we could have 2 of them. You with me so far? The problem is there are a lot more ways to write this. What goes in the remaining blank? What goes here? It could be either of the other 2. It could be none or 1. So we have to consider those options. So we have to say, well, we could say it could be what were the probabilities concerned? 0.55 or 0.32. So it could be 0.32, or it could be 0.55. Right? This could be probability of 2 or more, probability of 1. 2 or more, none. Are we with me so far? The problem is that's not enough. Because now we have to consider, what if it wasn't the first person I talked to? It could have been the second person. What if, because order is going to matter here, What if the second person I talked to was the one that had 2 or more semesters of calculus? So I could have put the 1, 3 here. Now what goes in the other blank? 0.32 or 0.55. Now, if you added all of those up, you would end up with 0.2431. Try it. You should get it. Do it for me. Someone do it, please. Multiply them all out and add them together. Put parentheses around each of these guys. It's fine. You should get the same thing as what we got in the original problem using the complement. Double check me though. Because if we didn't, we missed a situation. We missed one of the scenarios. But I think 0.2431. I think you should get the same answer. Right. So we got the same thing, right? Here's the issue. I don't really care if you want to come up with all the different possibilities. You're going to get the same answer. That's fine with me. But what if now I have 3 people in my group? What if I have 4 people in my group? Do you see how the more people, the more different possibilities the numbers can be put together? And the likelihood of you missing one of those scenarios is very high. So what we want to do is think outside the box, think differently, and think about using the idea of the complement. Okay? Remember that at least 1 means 1 minus the probability of none. Okay? Yes? No? It gets better. I trust you. Trust me. I trust you. It gets better. It does get better. This is a hard, that to me was a hard problem. Let's see. So I'm glad you asked that. Good. Okay, how to get 87? So 87 means that they do not have 2 or more. So 2 or more was 0.13. Not having 2 or more is a complement of that. 1 minus that is 0.87. 1 minus 0.13 is 0.87. Right? It's a complement. Not this, it's just 1 minus that. We're going to formalize that idea in a minute. The more you do this, the better it will get. I understand that it's uncomfortable right now. I get that. Right? It's okay. All right. If you would, go ahead and staple your homework together for me, and let's put it in the big chair. Okay, I'll go ahead and collect that. We are going to take some formal notes on probability in a couple of minutes. However, what I'd like to do is to look at your test. I'm going to pause the recording for a minute, and we'll come back to probability with that. Because you are going to have a Chapter 14 quiz on Friday. Next class. Next class, you have a quiz on Chapter 14. Right? So I'm hoping that today clarifies Chapter 14 a little bit. Right? So let me tell you that what's on here is not important to write down right now. I really would much rather you listen and be a part of the conversation, and then you can print them off at home if you want, or I will get to the part where it's important to write down, and I'll tell you. Right? Like there's an example of Venn diagrams that you should probably write down. But I want to talk about the difference between, there's 2 different kinds of probability, and I'd first like to talk about a theoretical probability, and we're going to start there, okay? And then we have something called an empirical probability, and that's based on like an actual experiment, or maybe it's a probability that we found doing a simulation, right? Think about Jordan's, where did he go? Oh, you just came in. Remember how on your test you started in a different place and you had a 0%? Everybody else got 75%. Remember on the test where you got 75% of getting at least 2 girls or something like that was the question? So based on a simulation, we can have a probability, but that's called empirical. The theoretical probability is when I know every possible outcome in a sample space. Should probably define that too. And then we look at a specific outcome of that sample space. So what do I mean by sample space? When you were reading and you did your thing, what is meant by that? What is a sample space? Yeah.
It's like the trials.
It's all possible trials. Okay? So it's all possible outcomes written out. And we'll look at that. For example, if I flipped a coin, what is the sample space space of flipping one coin? Heads, tails. That is the sample space. If I roll the dice, what is the sample space of rolling one dice? 1, 2, 3, 4, 5, 6. Just listing out the possible outcomes is all I'm looking for. Okay, that is called the sample space. We'll look at some more creative sample spaces. Obviously, they're not going to be that basic all the time. Okay, so we know a couple possibilities here. A deck of cards. What is the sample space? Nope, all sample space. The whole entire thing doesn't count anything. You have a deck of cards. What's the sample space? 52. The sample space would be the 2 of hearts, 3 of hearts, 4 of hearts, 5 of hearts, 6 of hearts, 7 of hearts. We list all the possible outcomes, right? It would take a while, but you know there's 52 of them. Okay, good. We know in a deck of cards, if you don't know this already, please write this down. But this is kind of, I assume this to be prior knowledge. We kind of have to, I think some of the problems we had to do dealt with that. There are 26 black cards. Half of the deck is black and half of the deck is red. Okay. Within the black deck or the black cards, we have 13 spades and 13 clubs. Yes. On card. Yes, we're not talking about those. We're talking about 52 decks. 54 decks would be those. Okay. So we have within black cards, we have 13 spades and 13 clubs. And then we also have 26 red cards, 13 diamonds, and 13 heads. This is, in this case, what did I say? 13 diamonds and 13 hearts. That's all what I meant to say, not what I actually say. I'll hear that much. So that would be a way to describe the sample space if you wanted to. Okay, we could describe it that way. It's something also that we'll look at a little bit later, probably after the quiz on Wednesday, at looking at, remember how we had talked a little bit on last class, we didn't record this part, about how with replacement versus without replacement. We'll talk more about that on Friday. But it comes in handy with the cards as well. But I just wanted to kind of describe this, because we come back to this reference quite a bit. So, what's an empirical probability? That's like what I was describing with actually conducting an experiment, actually rolling the dice and figuring out the probability of something happening. Conducting a simulation and actually finding out the probability based on a simulation or an experiment. It's actually doing something. It's not the theoretical probability. It's the actual what you're physically doing. Okay? So, rolling a die twice. What would the sample space be? How is that different from the sample space of rolling one die? You have to list the outcomes. Okay, so be careful. More than just double. Yes. Let's list them. Let's describe the sample space. Go ahead.
So you have 1 and 1, 1 and 2, 1 and 3.
So you can have a 1 and a 1. Okay. You can have, I'm going to write it in order here, not really, just to kind of just to separate it, honestly. You can have a 1 and a 2. You can have a 1 and a 3. You can have a 1 and a 4. You can have a 1 and a 5. You can have a 1 and a 6. Is it all of them? No. Now I have to go 2, right? So I had to list them all, wouldn't you say? Okay? So rolling a die twice and listing out, so I would say dot, dot, dot. There's definitely a lot more than that. Do you agree? Sample space is large. Okay? There are 36 possible outcomes, and I have in fact listed them here. Okay? You don't need to write all this down. But I want you to notice a couple of things. Okay? Okay, there are only 6 doubles, sure. Notice this one. Maybe the first.
If the dice are rolled in the same place.
If they're not rolled in this specific, you're playing Yahtzee. You know, you roll them all at the same time, right? So it's a little bit different. Here, I'm saying you're rolling a die 2 times. A little bit different than rolling 2 dice, don't you think? Because you have the probability would be different in those cases. Okay, because the order is going to matter. So you really have those little nuances of taking 1 die and rolling it twice versus taking 2 and rolling it at the same time make a difference. Okay, good. probability. So I'm going to unhighlight these because when we have a sample space listed as though we do here, we can use our sample space sometimes to come up with probabilities. So what's the probability I get a 1 on the first roll and a 1 on the second roll? Well, a 1 and a 1, I'm sorry, 1 and a 1 is this guy right here. Let's agree. That is 1, is that the only time that happens here? Okay, so that is a 1 out of 36. So sometimes we can use, I wonder if that's even here, let's see. Haha, look at me, I'm all like, cool. All right, so 1 out of 36. How about a probability of a 3 on the first roll and a 3 on the second roll? Is there only one of those two? All right, I believe that's true. Let me erase this guy. An even number on the first. Oh, look at me. All right, anywho, whatever. Oh, now it is. All right, fine. All right, and even is just half of them. Would you agree? I mean, half of them have even numbers on the first roll. We don't care about the second one. It's half. All right, a 7 on the first roll. Doesn't happen. Is it okay to have a probability of 0? Probability of 0 means it never happens. Okay? What's the probability that something always happens? 1. So a probability is always going to be between 0 and 1. Okay? And that is something that is you probably should know if you don't want to write that down, but I would. Probability 0 it never happens. Probability 1 is it always happens. Okay? Good. All right. The empirical probability is something sometimes it's called experimental probability. I don't really care too much that you know that. Really, you're just looking at your sample space of your outcomes and using it. So that's really all I'm caring about here. Okay. Now, this is an idea that you should know. We're actually going to end up proving it next week. Independent trials. Okay. How can I tell whether or not two events? Now, an event would be rolling a 2. An event would be, like back in this other example here, an event would be rolling the same number twice. Okay? So, in other words, all of these. Anyway, that would be an event. Okay? So, does one event affect the other? Okay? Think about rolling a die. If I take the same die and I roll it, pick it up and roll it again, are those rolls considered independent? Yes or no? Sure. Rolling a 1 the first time has no effect on whether I'm going to roll a 1 again. Would you agree with that? They're kind of independent of each other. Sometimes does one flip of a coin affect the next? Maybe. Can you think of a situation? There's only one, and it's not very common, but one situation where that could affect. Do you have an idea? You're a magician, and you yeah, sure. Take with your hand. Sure. What about the coin itself? What could be wrong with the coin itself? It could be double-sided. Sure. That's a great one. It could be what's called an unfair coin. It could be bent. It could have a weighted, one side's weighted in the other, and that's a lot of times magicians actually do that, where they actually weight a coin heavily on one side, so the odds of it coming up are more. So oftentimes if we talk about coin flipping, I will say a fair coin, and that just means it doesn't have any of those advantages. It's not bent, it's not weighted, anything like that. Okay. What about number 2? Is that independent, yes or no? Read the situation to yourself first. You got a decision? Stand up if you think they're independent. Stand up. I think they are independent. Stand up. All right. 1, 2, 3, 4, 5, 6, 7, 8. starting? Yes, no. You're not even starting. Okay, good. All right. How about if you think they are not independent? Say yes. You might already kind of do. One, two, three. Feel about half and half. All right. About half and half. We definitely don't have a unanimous decision here. For those of you who think they are independent, someone be the representative, be the voice of that group. Who thinks they're independent? Tell me why. Hunter.
One thing the bird flies into one engine, the other engine just
Okay. Maybe. Those of you who think that they are dependent, go ahead. Yes.
If one engine fails, the other one's gonna work. He's gonna have to work harder.
Yeah, that's what we were all thinking.
Right? So if one engine fails, we turn it off. Now the other engine has to work twice as hard, right? So that is an example of an actual of a dependent situation. Where it doesn't always, it's not very obvious at first, right? Sometimes you think, well, one's not going to affect the other. They're two separate, totally separate things. Oh, yeah. I'm sorry. It should be on the same plane. Yeah, I should specify that. Yeah, it has to be on the same plane. Okay, thank you for saying that. Never even thought about that. I'm not trying to trick you. It's on the same plane. All right. How about number 3? What do you think about number 3? We have a jar of jelly beans, almost jelly beans. My favorite. If we pick one red. Okay. Oh, this is important. Hang on. Let everybody read the question first. Okay. I like Hunter lessons. What does it depend on? With replacement versus without replacement. That really does make a difference. If I decide to eat it, is it dependent or independent? Definitely dependent, because the probabilities are going to change. But if I say, ooh, I don't like that one, put it back. What am I going to have to do to the jelly beans to be able to make sure? Because if I put the one back on top, the likelihood of taking that one back up is pretty high, right? We'd have to say stir it again. Is that what you were going to say?
I didn't use it for cinnamon. I was going to say if they're all red.
Yeah, they don't. Okay. We're going to come back to this idea in a minute. What if I had a gazillion jelly beans? What if I got like the Jelly Belly factory, okay? And I got a jelly bean pit the size of this room, and I pick one out. What do you think about that? Is the probability going to change whether I eat it or put it back?
Yeah.
So minutely and so minusculely it won't matter. So the bigger number of things you have, it's not going to matter. All right. How about number 4? Oh, with replacement. So this brings us to the idea of the law of large numbers. And a couple of the questions you did for homework, I think the first few questions dealt with the law of large numbers, didn't it? It talked about, it just provides a guarantee that as the number of trials increases, that the actual probability gets closer and closer and closer to the real probability that's going to happen. Think about your simulation for at least 2 girls. Right? Think about any simulation that we've ever done. The smaller number of trials that we have, the probabilities aren't that great. But the more trials we do, the law of large numbers says we're going to get closer and closer and closer to the actual probability, right? So that's kind of what this is saying. Okay? Just don't confuse it with what we call short-run behavior. Remember, like the weather person, we're due for a storm, or we're due for a hard winter, it's been a while, or that doesn't really happen, does it? So don't confuse those two things. Okay. So just a notation, okay? You don't have to write this down yet. I'm going to get to the point where we're going to have to write some stuff down. But when we talk about probability, I use a P, and then what's inside the probability is the probability of that event. Okay? So this is just read, the probability that I get tiger is 30%. That's all, this is notation. P stands for probability. What's inside the parentheses is just the outcome I'm looking for. Okay? To Here's something else. Probability should be given as a decimal, not a percentage. Okay? Sean? Are you sure? Okay. If you think about it, let me know. Okay? Probability should be given as a decimal. We don't say the probability of something is 30%. We usually say 0.3. Okay? It is always between 0 and 1. And we already talked about the probability that it's 0 is never happening, and the probability of 1 is always happening. This comes up several times and will come up in your homework as well. Probably comes up on the quiz. If you have a bunch of probabilities and they add to be greater than 1, what's the problem? There's a problem. We're going to look at an example like that in a couple of minutes. Okay? All right. We already know what a sample space is, so we're good. We already have discussed the idea of complement, but I want to talk about notation. I want to talk about the notation. Each book is a little bit different, and AP kind of wants us to know several different notations. But this little C here does mean complement. Sometimes you will see, like if you ever took geometry, like we have like not A, we had this little not squiggle, remember that? Not. Sometimes they did it this way, depending on, I think it's a little bar like that sometimes. There are other notations, is what I'm trying to get at. Okay? But our textbooks tend to use a little C to mean complement. Okay? The probability of an event happening and its complement always adds to be 1, which is, Eddie, what you were asking me in the homework at the beginning. How'd you get to 87? I subtracted it, right, from 0.13, or 0.13 from 1. Notice that the Venn diagram here, if we have an entire sample space, the complement is just what's on the outside. Okay, they just add to be 1. We're going to look at this idea of a Venn diagram in more ways than one in a minute. If the probability of failing the next success is 40% or 0.4, then it better not be that high. Kind of, we'll just pretend, okay? What's the probability of failing? Of not failing, sorry. 0.6. So you have a 60% or 0.6 probability of not failing, just 1 minus that. Pretty easy. So, this is the addition rule. And I kind of gave this to you, and I told you it was on your formula sheet. There's something missing, though. So look at the formula that I have here. And I want you to think about this formula only goes with one of these two Venn diagrams. It cannot go with both. So what's the only one that it could go with? Yeah, it has to go with this one. Because if you look at your formula sheet on the inside, and I so very, very rarely, by the way, will ever do this. I almost always will give it with its full counterpart. Remember last class I talked about this probability of A and B is the probability of the intersection, correct? Okay? So if they don't intersect, that probability is 0, which means if they don't intersect, the Venn diagram looks like it is on the left. There are 2 words used to describe this: disjoint and mutually exclusive. They are both used and they both are necessary. Okay, so it's just some vocabulary that you need to know. Okay, if 2 events have 0 outcomes in common, okay, I would use an example, and people always kind of like find holes in it, but you can't be both a boy and a girl at the same time. Yes, I know there's some acronyms, but I'm not talking. I'm just saying, like, you know what I'm saying? Like, let's pretend, okay, that they don't have any outcomes in common. There's no overlap there. Okay. Can you think of other types of mutually exclusive or disjoint events? Is it louder? Can't have your cake and eat it too. Sure. If you eat the cake, right? Okay, that means that they don't have any. Yeah. Can't eat it too. I like that. Anybody else? Louder. Okay, so I'm at Stonewall Jackson High School. I am not at Potomac Mills Mall, right? That is true. You can't be both at the same time. Those are, so being at the mall and being at school are disjoint events. Can't be both at the same time. Good. interchangeably, which is what I hate. I wish I could say that one's preferred over the other, but they're not. All right, so let's look at this. This is not the example you necessarily need to write down, but if you want to, you can. It's the next example that's important. If I have red, yellow, and green jelly beans in a jar, and I'm giving you these probabilities, okay? How do I check to see if they are disjoint events? Are they mutually exclusive? Yes or no?
Whether or not the probability of each of them is high. If each outcome is affecting something.
No. That is the idea of dependence, which is not the same thing as mutually exclusive. And I'm so glad you even said that because everybody confuses the two.
Oh.
Disjoint and mutually exclusive simply means they can't happen at the same time. If I pick a red green, I just messed you up. If I pick a red jelly bean out of the jar, I did not pick up a green one. It did not happen at the same time. They are disjoint events. I cannot reach into my hand and pick a jelly bean that is both red and green if all I have in the jar are red ones, yellow ones, and green ones. They are disjoint events. Are we okay with that? Okay. So, what is the probability that a randomly selected jelly bean is red or green? When I say the word or means we're going to do what? What operation does or imply? Add. Okay? And implies multiplication. Or means add. That is one huge concept for today. Or add. So red or green. Notice my notation. Red or green. Or, sometimes we use a U to represent or. And sometimes we represent with a little upside down U. You probably have seen that notation before, I hope. Okay, well you should have learned it in geometry. Let's use geometry. These and U's can kind of hit. It should be used though. I know, but it should be used. All right, so how do I do that? We know they're disjoint. There's no overlap to subtract off. So it's just simply going to be the probability of red plus the probability of green. Because there is no red and green, right? So it's just simply going to be 0.4 plus 0.25 or 0.65. Before I even do this, what should I probably have done to begin with? Not quite yet. Venn diagrams if they do overlap. What should I do with these two numbers? Or three numbers? That's what we should do. Do they?
Yeah.
Okay. I didn't check that first, but you should check that. Do my probability sum to be 1. Okay? What's the probability that a randomly selected jelly bean is not red? What do you think? Not red. It's just the complement, right? So the probability of not red, or we can say red complement, is just 1 minus 0.4 or 0.6. Good. All right. Here's the problem I'd write down if I were you. Okay? What happens if the events are not disjoint? Okay? So Amanda has a good point. I'm looking at the probabilities of owning a pet. I have the probability of owning a dog is 0.65. The probability of owning a cat is 0.45. And the probability of no pets is 0.2. And Amanda, what was your first comment? And I love it. They don't add up to 1. They add up to more than 1. Which means they can have a dog and a cat. Means that they are not disjoint events right now. Okay? So we have to draw a Venn diagram here. Yeah, that's a good way to do it. But you can have a dog and a cat too. Yeah, exactly right. So here is the key, and I'm going to try very hard as I go through each day and we do a new concept of probability, is how I've already said one today. Or means add, right? Another thing that's important here is if you see in a question the word both, that implies you should probably draw a Venn diagram. Okay? So these are just keywords to help you know the strategy to use. We're going to do a different one every day. Okay? So let's draw a Venn diagram here. So I know, because I have already checked, they added to be more than one, that it is possible to own a dog and a cat. So I'm going to say dog here. I'm going to say cat here. And none would be, I'm going to go ahead and just fill it in. I already know that none is 0.2. Would you agree? Okay. How can I figure out the numbers that go inside of that Venn diagram? There's a way to do it. Here's a strategy. I know that this number plus this number plus this number have to add up to what? No. 0.8. Where does 0.8 come from, Brenda? Because if none is 2, or 0.2, then all these have to add up to 0.8. Because everything in the Venn diagram together has to add to be 1. Are we okay with that part? Okay. So, let's think about what the rule is. The addition rule. The addition rule says the addition rule says the probability of dog plus the probability of cat minus the probability of dog and cat. Probability of A plus the probability of B is the probability of dog plus the probability of cat. Okay, let's get your formula sheet out. I don't need to. Get your formula sheet out. You should have it. Let's look at A's and B's. Anyone have theirs handy? Thank you. All right. So, if you look at yours, I'm using D and C rather than A's and B's. That's the only difference, because I'm doing dog and cat. Whenever you are looking at a contextual situation, you need to change yours. Don't use A's and B's like the formula does. Okay? What you need to do is use dog, cat. So that's why I'm using D's and C's. Do you see where the formula is coming from that I wrote across the top?
Yeah.
Are we okay with that? What does it actually equal? It's the first formula on your formula sheet for probability. It's going to equal the probability of dog or cat. Do you agree? Dog or cat is everything added up in here, which we already know has to be what? 0.8. So I already know that it has to sum to be 0.8. You with me so far? The probability of dog is 0.65. The probability of cat is 0.45. I'm going to subtract off what I don't know. What I don't know is this. That's going to be my x. Is that okay? So, if I add these together, I get 1.1 minus x is equal to 0.8. If I subtract 0.8 from 1.1, I get 0.3. So, I've answered the question. What is the probability of owning both pets? 30%. What I'd like us to be able to do is to fill in the Venn diagram as well, because then we can answer some other questions. Like, what is the probability of owning only a cat? What's the probability of owning only a dog? Those kinds of questions. So, let's fill in what we know. If I know that owning both is 0.3, how do I get the probability out here of owning only a dog? Well, the total of dog is 0.65. Subtract 0.3 and I get 0.35. So that goes here. What is the probability of owning only a cat? 0.3 subtracted from 0.45, and I get 0.15. All of these numbers, everything I see in red in my Venn diagram, should add to be what? 1. Okay? How do you feel? Well, we did this. You actually kind of did a little bit like this in geometry, a little bit while ago. A little bit. Okay? We didn't attach it to a formula. We didn't attach it to probabilities. Okay? Here's something that I need you to know before there's one more, I'm going to do two more things. Okay? Please realize that the or statement, one or the other happening, is simply the sum of everything inside the Venn diagram circles. Are we okay with that? Okay. That's where the 0.8 came from. Because I knew it was the complement of none. Right? All right. The one last rule that we need to address, we kind of already talked about, is the multiplication rule that we talked about earlier. And the multiplication rule only deals with independent events. I didn't say disjoint. I didn't say mutually exclusive. I didn't say they couldn't happen at the same time. I simply meant one engine failing is not going to affect the other one failing. Well, they have to be independent events. We'll talk what a dependent event is after you're quiz. But all you have to do is simply multiply the two events together. What's the key word that will tell you to multiply? And. If I draw a red card and a black card, okay, what's the probability of that happening? With the word and. A common example would be, if we're talking about cards, what's the probability of drawing an 8, let's do a jack of hearts. A jack and a heart. Let's do 2 cards. A jack and a heart. If I draw 2 cards, not 1 card, not a jack of hearts. That would be just one. There's only one of the deck, right? Okay, I'm going to draw 2 cards. What's the probability of drawing a jack and a probability of drawing a heart? Well, here's the question before I can even go any further. Are they independent events? Depends on with replacement versus without replacement. But we have to say it's with replacement in order for us to be able to do this, okay? So we're going to say we draw one, we replace it. So we have to say with replacement. Because otherwise it would affect something. Would you agree with that? All right, so with replacement. All we have to do is multiply them. What's the probability of getting a jack? There's 4 out of 52, which reduces to 113. What's the probability of getting a heart? A quarter of that. And then you would simply multiply the fractions together. Okay? So, what's 13 times 4? So 1 out of 52. Oh, that's interesting. Isn't that the jack of hearts? Oh, what? Okay. Anyway. All right, so you have homework to do. We're not going to do it. We're running out of time. So I want you to do 23 through 29, 31, 33. I realize that there are odd problems here, and the odd answers are on the back, which is why I'm saying show the work. Did you use the addition rule? Did you use the multiplication rule? Did you draw